Department, LD College of Engineering, welcome you for the last day of this 5 days faculty development program on advances in earthquake safe design and construction practice conducted under AICTE Training and Learning Academy. I am definitely sure that all the sessions of the last 4 days helped you all a lot in enhancing your knowledge to a level up. For making our last day more special and fruitful, we have Mr. Bhavin Shah, who is the founder and CEO of SQV Consultants. Sir has an experience of 2 decades in different engineering organizations. Sir has completed graduation in civil engineering and masters in structures from Sardar Patel University. Sir has a unique experience of working in the specialized firm of civil structural consultancy, which grew as a multidisciplinary firm, large multidisciplinary firm, and owner-based engineering setup. Sir had worked in different organizations at different levels, starting from junior design engineer to CEO. With a vision of enhancing the engineering profession, recently he has launched an innovative company named as SQV Consultant. Sir started the journey as a structural engineer and got the opportunities for designing industrial structures of the diversified industries like oil and gas, thermal power plant, renewable energy, manufacturing industries, etc. within India as well as outside India. Sir has also conducted many technical sessions across the country for knowledge sharing. Sir is pursuing PhD in structural engineering and his area of focus for research is to implement buckling restraint braces for earthquake resistant design of upcoming industrial structures as well as for retrofitting of the existing industrial structures. Now, I would request Mr. Bhavin Shah to grace us with his words of knowledge and experience on the concept of earthquake performance of steel structures and Indian code provisions. Over to you, sir.
Yeah, thanks a lot, Sandhya, for nice introduction. I'm sure that you're getting my voice clear.
Yes, sir, you are audible.
Great. Okay, so very good morning to all of you. Let me thank first of all LD Engineering College and Dr. C.S. Sangvi. I think he is not present here. Okay, I think he has joined for giving me this unique opportunity to interact with all of you on this very, very interesting subject, which is very close to my heart. So whenever I'm talking about design of steel structures and the earthquake resistant design aspects, so there are so many things to share from my side. So when I started my graduation, I was very much keen to do practice in the design of steel structure. So one of the reason was that it's very easy to understand the property of steel because it's a single material, unlike RCC. So since beginning of my study, graduation, post graduation, as well as in my practice, I was doing some kind of research and development work as and when time permits. Let's say from the very busy project cycle. Okay. So today's talk is regarding the performance of steel structures and how it is being dealt in the current Indian standards and what may be the way forward. So that's what in essence we are going to talk about. So I always like to keep the session as interactive as possible. So let's say in between talk, if you have certain queries, doubts, please feel free to stop me at any point. We will discuss. Okay. So let me share the presentation to start with. Okay, so I hope my presentation is visible on the screen.
Yes, sir, it is visible.
Yes, sir, it is visible.
Okay, perfect. So what we are going to discuss today in let's say in coming 1.5 hours. So we will initiate our talk with the performance of steel structure during North Ridge earthquake and how it has changed the perspective or let's say the overall thought process or let's say the overall design cycle for the steel structures. Then we will talk about section 12 of IS 800/2007. Then there is a third point which we'll touch upon, changes which are made in NBC 2016 for the design of steel structures, for which still a majority of the practicing engineers are not aware of. So I'll just touch upon that area. And then we will go to the quick overview of IS 1893 Part 4 2015. Because whenever we talk about steel structures,
ఈ రోజు అది వాళ్ళు ఇంటర్నల్ వాళ్ళు ఐక్యూఎస్సి వాళ్ళు అది ఉంది ప్రిన్సిపల్ సార్ ఎందుకు మనకి
I think mic needs to be muted for someone. Yeah. Okay, so whenever we talk about steel structures, then majority of these steel structures as of today will fall under the category of the industrial structures. So when we talk about earthquake resistant design for the industrial steel structures, then IS 1893 Part 4 2015 will come in picture. So we'll touch upon that part. And then I'll just quickly brief about the buckling restrained braces on which I am doing currently some kind of a research work on this. And finally, a few concluding remarks from my side. Okay, so this is something I have gathered, but please feel free to put up any kind of questions, doubts, etc., whatever you have during this session, or please you may also simply unmute your mic to interact with me during any part of the session. Okay, so let us begin our talk with this Northridge earthquake and steel structures. So this is the common statement. Whenever we talk about steel structures, then the steel structures are considered as relatively safe for the earthquake resistant design, right? Because it is more ductile material as compared to, let's say, the RCC, which is reinforced cement concrete. And that's why whenever we talk about earthquake resistant design, steel structures may be a good option as compared to RCC. But what happened in the Northridge earthquake, which occurred around 1994, it actually challenged this thought process that the steel structures are not vulnerable during the extreme seismic event. So what happened following that earthquake? A number of steel moment frame buildings were found to have experienced brittle fractures of beam to column connections. Now just focus on this area. The failure mode was the brittle fractures of the beam to column connections. And it was not just only in one or two buildings. Many buildings were having this kind of a failure, which was a brittle fracture. And if we just quickly take the statistics of the building, then height and the age of the damaged buildings, we can say it was ranging from 1 story to 26 stories. And age spanning, we can say that the buildings were as old as 30 years to the structures being erected at the time of the earthquake itself. So it's a quite diversified range of the structure which were damaged. Yeah, and again, it's important that no steel building suffered a catastrophic failure. Let's say that took lives in that earthquake, but some were so badly damaged they had to be demolished. Now, if the building is, let's say, completely damaged, and if it's required to be demolished, then we can understand that's a huge financial loss, right? And if we talk about the industrial structures, maybe in oil and gas, thermal power plant, etc., then it's a huge loss in terms of revenue, in terms of property asset of the country. So what happened in all the damaged building? So there was one peculiar failure, which was weld connections cracked in the beams and columns of at least 90 such buildings. Okay. Now, whenever we are designing for the earthquake resistant design, right, as you all know that what is the expected damage, always we look for a kind of a moderate yielding, and let's say it may be localized buckling of the steel elements. But the actual damage was the brittle fracture at the beam column junction. And and obviously, let's say whenever the beam column junction fails, so then the structure doesn't have a capacity to take more lateral load, maybe due to functional requirement, or maybe it may not be fit for taking the next cycle of the earthquake. So these all connections are required to be repaired. But at the same time, this damage was not at all expected. The brittle fracture at the beam column junctions. Okay. So let's try to understand quickly what happened in 1994 earthquake and why these welded connections failed. So the typical welded moment connections, or moment resisting connections prior to 1994 earthquake is shown on the screen. And here I think you are able to see that fracture is written. And that's the line which is shown as a crack, which is the kind of a crack which occurred in the welding. So what is our overall design philosophy whenever we are designing for considering the earthquake resistant design concept? That the structure should be able to take, or rather able to withstand, higher amount of displacement, because actually we are reducing the earthquake force by response reduction factor, and we are performing generally first order elastic analysis. But in actual during extreme seismic event, the force would be substantially higher, and because of that the displacement which structure has to withstand will be very much high than the displacement what we get from the first order elastic analysis, right? And that's why the structure has to be ductile. So here, if this joint is not able to withstand the higher amount of displacement in the structure, then the whole concept will not be able to meet its requirement. So what it says that if inadequately constructed, then these welded joints in the moment frames can become a weak links. And that's the failure we can say, which is the premature failure, okay, because it's not expected. So before we get to the next slide, let's try to understand what went wrong actually with this welding detail. This welding detail was conceived nearly, I think, around 1950 or 60s. And then the same welding detail was applied, or rather was considered in the different structures. Now, what has happened, let's say up from 1950 to let's say 1960s, 70s, 80s, as and when time progressed, the quality of the raw material has increased for the structural steel. The manufacturing process have also getting kind of a stabilization, so that the quality of the steel structure which was manufactured was having a superior quality, and with that the strength of the raw material, or let's say the strength of the structural steel, structural cross section, has increased over the time. Now what has happened, the welding detail which was conceived, let's say in 1950s, so welding details along with the electrodes etc was not at all updated. So what has happened that in the actual, now if we talk about the actual building, the cross section of the steel has got a higher strength as compared to the welding, and that was one of the probable reason for having the failure in all this welded connection, because welding itself was under designed. Okay. Now let's say if there is a damage, connection damage in any structure. Now, in order to determine whether building has sustained the connection damage, it is necessary to remove all architectural finishes, fireproofing, etc., whatever has been applied, and then performing detailed inspections. Now, let's talk about one of the industrial structure, and let's say one of the extreme seismic event has passed. Now, inspecting each and every connection itself is a very tedious exercise, and we do not have any set protocols like how we will identify, let's say, just by merely visual inspection, whether my connection is adequate or not, unless and until it is having some kind of a major distress which is visually appealing, or let's say visible. And that's what is written in the last line. Let's say even if no damage is found, this is a costly process, and again repairing of the damaged connection is even more costly. And that's why after this event of 1994 Northridge earthquake, there the entire welded connection, typical welded connection, was revised significantly. That was immediate improvement. And thereafter, around 120 to 130 connections, steel connections, were tested full scale. So, and based on that, a pre-qualified connections have been developed. So what happens, like if I get a certain size of a beam, for example, then what should be the column size that is fixed? Or similarly, if I have certain column size, then the beam size is fixed. So accordingly, the considering all permutation combination, the 120 to 130 full scale connections were detailed out, and based on that, a detailed pre-qualified connections guideline was developed. So as a practicing engineer, I simply have to take up the connection as a like as if I have my own library. So no changes are acceptable. It's directly pick up and drop into the drawing, and that connection is let's say kind of a fully tested connection, as well as further few more connections have been developed based on such experiments, research, and development. Now, let's say if we talk about India, we do not have any pre-qualified connections. And I think this is the major area when we talk about earthquake resistant design, because whatever kind of, let's say, advanced analysis and everything we do, but everything depends on the connections, in my opinion. And we do not have any set of pre-qualified connections as of today. So I think this is the major area which you may note down. Okay. So this was a quick discussion about history, what happened in the Northridge earthquake and how it has changed the perspective related to steel structure design. So when we talk about steel structure, then there is a section 12 of IS 800 2007. I'll tell you interesting story about section 12. So firstly, when Indian Standard Code was revised in 2007 or 8, and we were designing the first project considering the latest 800 2007. So at that time, my senior just came to me and then he asked, Bhavin, just look at this section 12. It appears that it is for the earthquake resistant design for the tall structures. So since 2008, I started looking into that section 12. And let me tell you honestly, till today, I am looking into the section 12 because I'm receiving so many queries, let's say from outside as well as from the inside, whether section 12 is applicable in certain structure. If section 12 is applicable, then which clauses are applicable? And let's say certain clauses are applicable, then how to implement those particular clauses in the software. There are still many practical difficulties and ambiguities related to section 12. So let's see quickly what is the section 12 is all about. So it's part of IS 800 2007, right? And if we talk about IS 800 2007, it is having 17 sections and 8 annexures. And 800 2007 is covering all the different areas exhaustively, starting from material methods of analysis, limit state design, connections, and earthquake resistant design, which we will now just focus after a couple of minutes. Then fatigue testing, durability, fire resistant, fabrication, and erection. So it covers a very broad spectrum for design of the steel structures. So earthquake resistant design is just only a small part of it, which is section number 12. So section number 12 talks about earthquake resistant design. Now, whenever we talk about earthquake engineering, this is the way I see that these are three main pillars of earthquake resistant design. So one is the design, detailing, and then execution, and all these three pillars has to be given proper justice simultaneously. That means, for example, let's say if I have done very good design detailing, but execution is not done as per the detailing, then it doesn't serve any purpose. Similarly, let's say if design and execution is done, but detailing is not up to the mark, like connection detail, for example, then the entire perspective, or let's say the entire aim of earthquake resistant design will not be met. So these are the three main vertical which we should keep in mind when talking about earthquake resistant design. And as I told you that this is not a conventional revision of the previous code. There is a major change in philosophy in IS 800 2007. So there are so many practical difficulties. So right now there is one online course going on related to IS 800 2007, wherein we are discussing, debating each and every clause. And one of the major problem is that detailed handbook explanatory note along with the practical example is still not published. So that's why there are many questions in the mind of structural engineers. So, but what I always say that these confusions faced by engineers, let's say for the section 12 or the other parts of the code, if we try to understand entire philosophy of the code, then it is easy to understand and decode the individual clause and then how we can apply in the software. So we will touch upon a couple of clauses to understand in such detail. But of course, we can have more elaborated discussion, maybe if required in future. But right now, I'll touch upon the few important clauses of section 12, and I'll share my quick perspective related to different clauses. And we'll talk about a couple of clauses in more detail. So now we can say that now we are migrating from the force controlled design to the displacement controlled design in our overall design philosophy of the earthquake resistant design. And generally we are performing the first order elastic design, and these are the two major drawbacks. As we all know, that reserved strength cannot be quantified, and the collapse mechanism is not known whenever we perform only first order elastic analysis, right? Now, when you talk about section 12, what it says that the steel frames shall be so designed and detailed as to give them adequate strength, stability, and ductility to resist severe earthquakes in all zones without collapse. So this is the overall aim of earthquake resistant design as per section 12. So I always used to say that when we talk about section 12, it is nothing but it is ductile detailing for steel structures. Like for RCC, we have IS 13920, which is a separate code which is detailing out ductile detailing for the reinforced concrete structures. But for the steel structure, I'm used to say that the section 12 is ductile detailing for the steel structures. So let's have a quick overview of section 12, and we will try to discuss a couple of clauses in detail. So section 12 is for the earthquake resistant design, and it is applicable to frames which resist earthquake load. So now in, let's say in steel structure, all the frames are not designed for considering or rather for resisting the lateral loads, or let's say the resisting earthquake load in our today's context. So this section is applicable to frames only which are going to resist or which are designed to resist the earthquake load. Now, these are the different type of frames which are available in the section 12 and can be classified into two major category: braced frame and the moment frame. And when we talk about the braced frame, again, it is having three categories: OCBF, SCBF, and EBF. So ordinary concentrically braced frame, specially concentrically braced frame, and eccentrically braced frame. And for the moment resisting frames, it is ordinary moment frame and it is a special moment frame. Okay, so let's try to see what's the difference between all these frames and which frames can be provided in which zone, etc. So before that, just let me touch this one point. Now, section 4 of IS 800-2007 is talking about all different types of analysis, and wherein plastic analysis is also detailed out. So generally plastic analysis is allowed, like in IS 800 or BS 5950 code. So it is actually allowing the use of plastic design where loading is, let's say, predominantly static and fatigue is not a design criteria. So whenever we talk about earthquake resistant design, we can go for this plastic analysis. Now this plastic analysis is nothing but it's a kind of a performance based design. So it is already included in IS 800-2007 in section number 4, and this is I think the major area which should be further taken up in the industry for the cost optimization as well as for the for ensuring better performance of the steel structures during extreme seismic event. So what will happen if you will start considering the plastic analysis? So this is the this is simple diagram which I have just put up here. So as we all know that whenever we consider a simply supported beam and if we apply the concentrated load, then let's say up to elastic limit we will have the moment my. And if we consider it as a fully plastified or let's say full plastic cross section is utilized, so in that case the plastic moment will be 15% higher, right, as compared to the elastic limit. So this is the only one beam which we are talking about. But now when we talk about the real structure, so there will be more redundancy, so which will result into the higher strength using plastic analysis. And obviously, depending on the degree of indeterminacy, a number of hinges are required to be produced before the yield mechanism can form. So that will result actually a significant reserved strength beyond the elastic limit. So at present, it's not followed into the industry, but it is already there written into the code. And at least I am suggesting that we should prepare certain kind of guidelines for the practicing engineers so that it can be followed into the industry with more confidence. Now, when we talk about section 12, and as I told you that this is a kind of a ductile detailing, so more thrust is given to the connection design in section 12, and earthquake forces are generally increased by 20% for connection design. And also detailing of connection is also suggested for different types of frames. So quickly, if we talk about connection details as per section 12, then it is talking about complete penetration butt welds, okay, and high strength friction grip bolts or turned and fitted bolts to be used. The bolts are to be fully tensioned. And regarding weld, we have already discussed that all welds should be full penetration but weld except splice. So on other or rather no other type of weld is allowed. Okay. So whenever we come into the section 12 for earthquake resistant design, then this is the major area for the connection design we should take care, because it changes the type of bolt as well as the type of weld. Now this is a very interesting clause, which is para number 12.7. It is for ordinary concentrically braced frame. And let me tell you honestly, when I read this clause for the first time, I took at least a couple of years to understand, because every time I'm designing a new structure, I come to this clause, I start to rethink on this clause, but again, it was not getting very much clear into my my thought process. But after designing a few structures after 2008, slowly and gradually I started thinking about this clause, and I'll just share my own perspective, what I understand. And let me tell you honestly, this clause is simply or let's say silently ignored into the practice as of today. Now what it says, let's try to read out first. So what it says, that the ordinary concentrically braced frame OCBF should be shown to withstand inelastic deformation corresponding to a joint rotation of at least 0.02 radians without degradation in strength and stiffness below the full yield value. And ordinary concentrically braced frames meeting the requirements of this section shall be deemed to satisfy the required inelastic deformation. So what does it mean? First of all, it is talking about inelastic deformation. That's very clear. So it is talking about non-linear analysis, right? But what is the meaning of this 0.02 radians? And then again, what is this without degradation in strength and stiffness below the full yield value? And then how to do it into the software? So first of all, this clause cannot be compiled or cannot be considered using conventional first order elastic analysis. Now what it says, and from where this 0.02 radians have come up. So according to me, like during all these extreme seismic event, like let's say the Northridge earthquake event or other earthquake events, whatever occurred across the world. So at that time, actual joint rotation of different steel structures were measured, which were damaged, or let's say even if the building was standing, but the joint rotation was observed because of the higher deformation. So that joint rotation, I think, was in range of 0.05 radians or higher than that. So from that, these two values could have come up, which is 0.02 radians for ordinary concentrically braced frame. And now when we refer specially concentrically braced frame, all entire language is same, but it says 0.04 radians. And similarly for OMF and SMF, it is 0.02 and 0.04 radians respectively. So since OCBF, we will be putting, let's say we are allowing only up to seismic zone, or rather for the lower seismic zone, it is having value of 0.02 radians, and SCBF is allowed for the higher seismic zone, and SCBF also can be placed in the lower seismic zone if it is required. But that's why that radian is higher for SCBF as compared to OCBF. Now question comes, how to do it into the software. So firstly, we shall go for a non-linear analysis. That is first thing. And we should start applying the lateral load arbitrarily on the structures, or let's say whatever earthquake force which we have applied on the structure, that force value we should increase, and then we should see in each iteration that are we getting a joint rotation of, let's say, this 0.02 radians, or let's say the 0.04 radians, whatever the case may be, on each joint. And once we get a minimum value of this joint rotation on all the joints, at that point of time, we have to see that the whole structure is safe. For example, there is no degradation in strength and stiffness below the full yield value. So this is the one of the way this clause may be complied. But again, the most important part in this clause is the connection design. Now, when we talk about this 0.02 radians, let's say we have checked the member strength with respect to this application of the load, and then after performing the advanced analysis, we will be able to demonstrate the adequacy of the member or adequacy of the structure as a whole. But again, I'd like to highlight this point at this juncture, that for getting this higher joint rotation of, let's say, 0.04 radians, the connection also needs to be detailed out accordingly. So which is of course not documented presently in our code, but I think that's what is required. Okay. So another requirement for ordinary concentrically braced frame. So it is said very clearly that the K bracings are not permitted. Slender bracings are not permitted. Now here, this para number 12.7.2 is also creating a lot of debate, a lot of discussions, because it is restricting the bracing member with a slenderness ratio of 120 only. Now, what's the reason for this 120? So one of the reason is that whenever we talk about this earthquake force, so it is actually reversing, let's say, in plus x and minus x direction, right? So if we have provided let's the bracing in the structure, so that bracing member will have to take a compression in certain cycle, and then it has to take a tension in the reversal cycle. So when the compression force, when it will be applied on the bracing, and let's say, for example, the force has exceeded, because as we just discussed, the earthquake forces we are actually reducing to with the value of response reduction factor. Now let's say with these during extreme seismic event, if our bracing in the compression during the compression cycle, if it has buckled, then it won't be able to take the next reversal cycle, which will be coming through the tension, right? And because of that, there is a higher requirement of the bracing with respect to the slenderness. And probably this is one of the area where I am just working for my PhD work also. So I'll just brief you a little bit about it. Now, in OCBF, again, there are a few other requirements, that the utilization ratio in compression should not exceed 0.8, and the criteria for design of tension member is also defined here. And connection design criteria are mentioned for the bracing as well. Now let's go to SCBF, which is a specially concentrically braced frame. So as we discussed, for the specially concentrically braced frame, the first thing is the joint rotation 0.04 radians we need to demonstrate. And thereafter these other requirements are given. So for SCBF, first requirement is that the all sections shall be plastic, all braced cross section. And the slenderness of the bracing shall not exceed 160. And this only hanger, that means it is defined only for the bracing which are not taking part into the earthquake resistant design, or let's say these are just taking an actual tension. And the connection shall be designed to withstand a moment of 1.2 times the full plastic moment. So the connection shall be designed considering this 1.2 times the full plastic moment, and accordingly that connection needs to be detailed out. And for SCBF, obviously all column sections also shall be plastic. Okay, this is one more area where I would see that generally there is some ambiguity. So which is eccentrically braced frame. Now, as it figures shows and as the name shows, the eccentrically braced frame. So I was just recently talking to the group of practicing engineer, and at that time there was this wrong concept of EBF. So I'll just brief to you for your reference. So what is being understood that, let's say if I am providing my two bracing like this bracing which are shown in, let's say, first figure, eccentric. So let's say in a detailing itself, I'm not making my bracing concentric, but I'm making my bracing eccentric. So that frame will be considered as an eccentric braced frame. But that thought process is not fully correct, because as you all know that whenever we talk about EBF, actually we need to create a kind of a link beam between two connected bracing, and that link beam will absorb the entire seismic energy during the extreme seismic event, and rest all structural elements will remain elastic. So this is the overall philosophy or the overall concept of the EBF, which is not at all detailed out in our code. Instead, it is said that the specialist literature should be referred. Now, when IS 13920 was released, and then it has introduced the clause for the strong column and weak beam, and right now that ratio is 1.4. But when we talk about the steel structure, the strong column weak beam concept was introduced since long, in 2008, and that ratio is 1.2, which is detailed out in this para number 12.11.3.2. And one more area related to the design of column bases, which is creating a practical problem, because it says that the fixed column bases and their anchor bolts should be designed to withstand a moment of 1.2 times the full plastic moment capacity of the column section. And the anchor bolts shall be designed to withstand the combined action of shear and tension, as well as prying action, if any. Now, what happens if we really put the actual number, considering the full plastic capacity of the column section, then the size of the base plate and the anchor bolt are extremely high or unpractical to accommodate into that region. That's the common feedback which we are receiving regularly from the practicing engineer, and we also experience the same thing while following this clause. But the overall intent of this clause is that the base plate connection is also one of the location where plastic hinge could occur, and that's why that junction also needs to be detailed out with this requirement. But I think some more clarification is required in this clause. Okay, so this was quick discussion related to section 12. Of course, we have not discussed each and every clause, but I just took up few important clauses for discussion. Now here I have just made quick comparison with the older Indian Standard Code, which is 1984 code. And right now, let us talk about the design methodology. So as we all know, 800-2007 is limit state design method, and old IS code is working stress design method. So when we compare the member design, and if we consider IS code IS 1984 as a benchmark, then the member design may be economical as per 800-2007, or maybe similar in some cases. And it may be stringent in certain cases, because there are certain different limit states which have been introduced in 800-2007. But most importantly, when we talk about connection design, and if we make a benchmark as the connection detailing as per 800-1984, then the connection design is substantially stringent, as per 800/2007. And that's what I'm suggesting in a different groups to the practicing engineers whenever I get an opportunity, because there are many offices in which still the connection design is not updated with respect to the latest code. It is still prevailing with respect to the earlier code. So I just wanted to make this point here that the connection design is stringent as compared to the earlier code. Okay, just let's quickly touch upon this point, changes in NBC 2016 with respect to design of steel structures. So as we all know, IS 800/2007 was released, I think, in 2008, and thereafter it's only one amendment which was released, which is amendment number 1, and that was released in 2012. And this is the final document what we have as of today. But there is a major update to this. So when NBC was revised in 2016, so at that time, so I hope you must have gone through the NBC 2016. So in NBC 2016, majority of the Indian standard codes are reproduced. So when this IS 800/2007 was reproduced in NBC 2016, it was IS 800/2007 plus amendment number 1 plus there are improvements made in NBC 2016. So with this, NBC 2016 actually becomes the latest document for the design of steel structure as of today now when we are talking. So it is having 800/2007 plus amendment number 1 included, plus certain improvements are made in NBC 2016. So here I'll just give you the quick methodology, like how to read and compare NBC 2016 and IS 800/2007. So in NBC there is a volume 1, then there is a part 6 which is a structural design, and then there is a section number 6 which is for the steel design. So let's say, for example, if you have a para number 2.3.1 of IS 800/2007, then the same will be mentioned as a para number 8.3.1 in NBC 2016. Okay. And here I have taken this extract directly from the forward of the NBC 2016 for your quick reference, that this revision of the section is intended to bring it in line with the revised version of IS 800/2007 read with its amendment number 1 and to take care of further improvements and incorporations required. So in this revision, therefore, the following major modifications have been made. So here I have just taken a couple of extract from the forward, which is related to our today's talk. So what it says that the provisions related to design for earthquake loads relating to load and load combinations, response reduction factor for various types of frames, connections in the critical zones of the frames, and bracing members have been updated. So let's say whenever you're referring the section 12, then please refer the latest document which is there in NBC 2016. So whatever we have discussed related to section 12, that extract was taken from the IS 800/2007. So I'll advise, if you are referring this 800/2007, please keep NBC 2016 side by side. And this is the latest document. And here you can see that these differences have been made. So right now, because of time constraint, I'm not going into all the changes which are being made. But you can go through this NBC 2016. And then if you have any further doubt, you can always contact me. Also, the provisions related to non-ductile braced and moment resisting frames have been included. This is the statement I have taken from the forward. And one more thing, provisions on ductile designing with respect to the column based connections have been updated. So it is written here that the column based connection design have been updated, but when I was referring text to text of both the document, then I couldn't find any difference. But you can go through it, and if you find any significant difference, definitely you can highlight and then share it with me. Okay, so this was a quick discussion related to section 12 and then the changes done into the NBC. And again, now when we talk about design of steel structures, then IS 1893 Part 4 2015 is one of the most important code, because as I just told you, that majority of the steel structures what we are constructing in the India are for the industrial purpose, and that's where the IS 1893 Part 4 2015 comes in picture. So here you can keep a note on this, that now for 1893 Part 4 2015 also 2 amendments have been issued. So those amendments I have not included in this presentation. So while referring this presentation, please keep in mind that there are additional 2 amendments which you just keep with yourself for reference while reading this document. Now this is very important, interface between different Indian standard codes. So right now we are talking about interface between 800 2007 and IS 1893 Part 4 2015. Now why interface is important, and sometimes there are big philosophical gap between 2 different Indian standard codes, because the revision cycle of each Indian standard code is different, and the committee is different, and the years in which the revision is initiated and years in which it is completed, that is also completely different. And because of that, it is quite possible that there may be a certain philosophical gap, and each standard for getting revised, it is taking almost time of 10 to 15 years. So within that time, whenever the next revision comes, we get substantially higher amount of information, because whatever global industry has attained, or let's say the global accumulated intelligence has attained, let's say in the last 10 to 15 years, is being incorporated into the code or whatever is possible. And that's why we get a very steep jump whenever we get the revision, and that's why this interface is also very much important. So here also for 1893 Part 4 2015, I have taken just few slides to quickly understand how it is different and what are the different methodology which we need to adopt when we are talking about design of industrial steel structures as per IS 1893 Part 4 2015. So first it's talking about vertical acceleration. And what it says that the earthquake generated vertical inertia forces are to be considered in design unless checked and proven to be not significant. So for checking and proving that this vertical inertia force is not significant, we will have to apply the vertical seismic load. Okay, so that's the first part. And it says that the in steel structures, members and their connections should be so proportioned that high ductility is obtained as specified in IS 800, avoiding premature failure due to elastic or inelastic buckling of any type. So when it says high ductility, the go-to statement is section 12. Okay. And now it's talking about design spectrum. So for all majority of industrial structures, we are developing the design spectrum also. So it's a kind of a site specific spectra, and then the design will be performed as per the site specific spectra, as well as per the design spectra given in the Indian Standard Code, and accordingly the design will be performed. Now, when we talk about load combination, the IS 1893 Part 4 2015, load combinations are given for the plastic design. So we just touched upon one area related to the plastic analysis when we talked about 800 2007 section number 4, and para number 8.3.1 of Part 4 is giving the load combinations for the plastic design. And that factor is 1.7, you can see. Now, this is a very important table, which is table number 2, which is talking about earthquake force estimation, method of analysis and design for various categories of structures. So here in this table, it is talking about structural analysis methods and the structural design methodology for different categories of the structure. So category 1 is the most important structure and category 4 is the least important structure. And the most important part here, which I want to highlight, is that it is written that non-linear time history analysis for verification of mechanism needs to be carried out for this category 1 structure. And it says that whenever the plan-wise distribution of mass and stiffness is not symmetrical, then we need to combine the earthquake forces in all 3 directions. So generally for industrial steel structures, we will not have the distribution of mass and stiffness symmetrical. So that means the consideration of earthquake force in all 3 directions simultaneously needs to be done. Now this one more clause creating problem in the industry, which is for the soil structure interaction. And it says that the soil structure interaction may not be considered in the seismic analysis for structure whenever it is supported on the rock, or let's say the hard soil or the rock like material, when we say N is greater than 50 and shear velocity is, let's say, 760 meters per second. So in essence, if my structure is sitting on hard strata, soil structure interaction may not be required. But for all other cases, the let's say whenever it is sitting on soft soil or the medium soil, then the soil structure interaction is required. So majority of the cases, soil structure interaction is required. Now, how to do it? Of course, now there is a debate always happening between design consultant and the proof checking consultant, as well as the owner consultant. But this area we can discuss in detail if you are interested. But right now I'm just highlighting the different few of the important points, I would say, as per this code. And now it's talking about interaction effects between the structure and equipment also. So the interaction effect, that means the interaction effect between the structural primary system and the equipment secondary system. And then a very detailed process is given in the code that how this interaction effect can be considered. Now, this is also one of the area where the difficulties are being faced because there are no worked out examples. One more area I'll just touch upon related to the time period estimation. Now, what it says in 1893 part 4 that the formula given in IS 1893 part 1 for estimation of time period for buildings, which is para number 7.6, are not applicable for the industrial structures because industrial structures are highly irregular and they cannot be or maybe, or we can say in other words, there may not be empirical formula which we could have derived for the building kind of structures in part 1. So those empirical formula for time period is not applicable to the industrial structure. So that means the time period, whatever we get from the computer model, will be considered. And that's why I put this note with the red color that the time period calculation should be accurate. And there are several instances in our real projects wherein because of the higher time period, the earthquake force is substantially lower. Now, based on our database and based on our engineering judgment, we provide the internal scaling factor to enhance the earthquake force. So this is just one area I wanted to highlight. Now, the code says that the P delta effect is mandatory for all the structures and torsion also needs to be included in the analysis. So second order elastic analysis is now compulsory for all the structures. Now, in this para, the code is talking about the requirement of non-linear time history analysis for different categories of the structures. And the para number 10.1.1 is talking about this nonlinear time history analysis of structures subjected to seismic loads shall be performed for study of safety against collapse. And this is the only small para which is given. So this is also one area which needs to be detailed out for to avoid the ambiguity in the practice, because based on these the collapse mechanism needs to find out, and there are certain exercises going on in different organizations where I'm connected, that what is the actual impact of tonnage if we consider this clause, and let's say if we ignore this clause. Okay. One more point, very important point, I'll just highlight that in part 1 it is said that the damping is 5% irrespective of any material of construction, wherein in this code damping is still 2% for the steel structures. We can see in this first table it is 2%, and for the MCE case it is allowing higher damping ratio. But when the DBE, or let's say the damping is 2%, then uh, the multiplication factor for the obtaining values of zone factor is 1.4. Yeah, and this is the annexure B, which is talking about the weighted average of corrected N value, and at least shear velocity to be considered up to 30 meters. So with this, we can say that the borehole depth should be minimum 30 meters. Okay, so this was quick discussion related to part 4, 2015. Now just let me take a few minutes for buckling restraint braces. Now, if we take a quick review of the existing structural system for the structures, then we can divide it in two categories, right? So one is the conventional braced systems and another is the moment resisting frame. Now, both the system is having limitation, like if I am providing only moment resisting frame, then my structure is becoming too flexible and it doesn't meet the functional requirement of the drift, stringent drift, which is required because of the functional requirement. On the other side, if I provide a braced bray, then what is happening? The capacity of the steel member in tension is significantly higher than the compression. So whenever the reversal cycle will happen, the size of the bracing needs to be increased. Now, moment I increase the size of the bracing, the stiffness of the structure is increasing, and because of that, the time period will come down, and because of that, it will get a higher seismic force. Now, again with the higher seismic force, the force into that bracing will increase. So it's a repetitive cycle going on, and at the end, we tend to have a very bulky bracing. So that's where after designing so many structures, or every time I was thinking that there has to be certain intermediate structural system between, let's say, MRF and CB. And that's what, these thoughts were generating repeatedly in my mind while designing the complex structures in oil and gas, thermal power plants, etc. So while attending one of the workshop of Japan's Society of Seismic Isolation, I came across with the concept of this buckling restraint braces. So it is, in simple words, I'll tell you what's buckling restraint braces. It's a kind of a brace which is designed to consider similar kind of capacity in tension and the compression. This is the simple concept. And if we talk about history of BRB, it was when I was reading the history, actually the invention was started by the Indian and the Japanese engineer way back, I think in 1970s. And thereafter, the Japanese people took it forward, into the research and development work. But then no further work happened in India. But the roots, if we see, then it is in our country. And of course, there is also one of the BRB which was developed in Bangalore also. But we can say that this technology is now in the existence since last 30 years. And still numerous studies are being done on BRB across the globe for areas like low cycle fatigue, etc. So we'll not go to in the detail of the BRB. If you are interested, we can have a detailed discussion on this. But right now, just let me show you what are the different components of a BRB. So it will be having this steel core. This steel core will be resisting the axial compression and the tension cycle. And to prevent buckling of this steel core during compression, we will be having this concrete fill, and this concrete fill will be supported by the exterior steel tube. And the most important part, there will be a debonding gap between this steel core and this high strength concrete fill, or let's say the high strength mortar. Okay. But overall concept is to achieve similar compressive strength equal to tension strength, so that the size of the bracing is reduced, structure is also becoming flexible, and because of that there is a lesser seismic force on the structure. So it is very much efficient with respect to the conventional system. Okay, so just let me touch upon here. So if we talk about these unique advantages of BRB, then it is having symmetrical hysteresis, since it has almost similar capacities in the axial compression and tension. In fact, its capacity is little bit higher by, let's say, by 10% as compared to the axial tensile capacity, due to low friction between the debonding material and the mortar. And the another most important advantage of BRB is that they yield at the lower drifts. So they will yield actually before the main structural frame. So then so they can act as a fuse also in the structure. So the unique advantage of BRB, we can say that the one of the most distinctive advantage against the conventional braces, that the stiffness of BRB can be adjusted in such a way so that all stories of the structure will yield simultaneously. Now this kind of adjustment is not feasible in the conventional braces. So this is where I'm just walking right now, that this BRB may be included in section 12. Right now it is not mentioned in the section 12 as the earthquake resistant design system. And a design method that is becoming increasingly popular in Japan keeps columns and beams of buildings in elastic regions as much as possible by using buckling restraint presses as hysteretic dampers. These are the few pics of the installation of BRB. You can see rather these are all different kind of BRB. So BRB is actually, it's a manufacturer product. So that's why we could see it's all bracing is having a different kind of shape as well as a different kind of a design system. So whenever we talk about BRB, it requires a great interface between the design engineers and the BRB manufacturer. These are a couple of examples like how this BRBs can be placed into the structures. Even BRB also can be placed as a buckling restraint brace as a column also. This can be also used for retrofitting of the existing structures, right? As well as it can be provided for the new structures. Okay, so with this, let me put a few points before we open the session for question and answer. So again, I would like to stress this point, which is the connection design, that the connection design and detailing is vital for the earthquake resistant design of steel structures. And connection design should be in scope of structural engineer and not in the scope of agency for preparation of fabrication drawings. So this is the general trend which is occurring into the industry, which I observed into the projects. And whenever it was feasible, I curtailed it. I tried to change the practice. But what is happening? See, the structural engineer is preparing the general arrangement drawings, considering, let's say, the structural analysis, and then he will optimize the different cross sections, which is, let's say, beam, column, bracing, secondary beams, etc. Are being provided. Now this entire lot will be transferred to the fabrication drawing preparing agency. Now it is in the scope of the fabrication drawing preparation agency to detailing out the connections, and then to see whether there is any clashing or not, and then those documents will be again sent back to the main consultant for the review. Now if we talk about actual project, actually the fabrication drawings, as we all know, it is actually running into the thousands of drawings. Let's say for a typical structure we were receiving 5,000 fabrication drawings. So it is virtually impossible to review each and every drawing. And also all design offices may not have the license of the TECLA so that they can review the 3D model virtually. So with that, this is becoming one of the major gap area into the industry. And again, when we talk about the fabrication drawing preparation agency, they do not have qualified structural engineers. So they do not have any sanctity. They don't know what is 800 1984, what is 800 2007. So so that's why the connection design shall be in the scope of the structural engineer. That's what I have written here. And wherever I was into the charge in the project, so at that time we were making the scope demarcation very clear. Otherwise, let's say if the connection itself are becoming the weak link, then the whole purpose of the earthquake resistant design is lost. Even let's say whatever sophisticated analysis we have done, whatever kind of, let's say, members we have provided, but if connections are not adequately detailed out or adequately designed, then this whole purpose is lost. Okay. Second point is the quality of welding. Now, quality of welding is very crucial for the earthquake resistant design. And that's why it is suggested that the shop welding should be preferred as against the site weld. Now, whenever site welding is done, so first of all, there is no, we do not have a properly qualified welders. That is the first area. Secondly, that welding is not checked properly on the site. So the required simple quality checks for the welding are not performed at the site, because let's say if the welding is done at a height of 30-40 meter, now the supervising engineer will go at a 40 meter, and how much time he will be there. That's the one thing, that's for the supervision. And again, the quality checks which are required, kind of a NDT test for the welding, those are also being not performed generally on the site. And that's why the shop welding is always preferred, and that's where the connection detailing comes into picture. So yeah, as a practicing engineer, from beginning we should conceive majority of the shop welding, and just only minority of site weld maybe are allowed in the, let's say, less critical structural parts. And this is my one of the favorite slide. So we have not touched upon this area, but let me take a couple of minutes on it. Now, whenever we talk about earthquake resistant design and the Indian standard codes, then this software also comes into picture. And let me tell you openly that these software are not fully compliant with respect to the Indian standard codes. Now, the reason maybe the clauses may be ambiguous, or let's say the certain methodology or certain algorithm may not be available in the software. But sometimes it's not explicitly written into the manual of the software that such and such clause is not considered. So generally it is left to the design engineer, or let's say to the practicing engineer, that you should validate and authenticate the software. So this was my one of the role in different organization, as well as still today I'm doing out of my passion, interest. That we are trying to compare the software along with the Indian standard code clause by clause. And then we'll try to see whether a particular clause is appropriately included or not. And with this, we have our in-house list of the clauses which are not included. So whenever, let's say, the design is produced from the software, or let's say when the drawing is prepared, then we take an appropriate judgment or appropriate call uh, on those drawings, member sizes, connection design, etc. So overall, over and above software, certain efforts are required based on that in-house exercise. And that's why I've written the text in a red color, that the structural engineer should be aware about the limitations of the software being used while performing the design. And this is the quick way forward for buckling restraint braces, in my opinion. So there is a potential of using this buckling restraint braces technology for new as well as the retrofitting of the existing steel structures. And significant amount of interface is required between the engineer and the BRB manufacturer while the design process. Now, the most important point is this third one, that the strict quality control is required for ensuring the intended performance of BRB. So when we talk about that debonding gap between the steel core member and the high strength mortar, that debonding gap, when we calculate, actually that comes in a range of, let's say, 1 mm or 2 mm. Now if that gap is exceeding, let's say, beyond 2 mm, for example, then the capacity of the steel core will be lesser, because the compression, or let's say the buckling, will be allowed. So that's why the strict quality control is required, because we have to ensure the debonding gap of only 2 mm. And that's why after manufacturing of BRB, so there is a protocol in all different international code to have the full scale testing. And why full scale testing is required as per all different international standards, as per Japanese standards, American standards, etc., because there are number of variable factors into BRB, and each factor is quite sensitive, which can affect the performance, intended performance of BRB. And that's why I have said that it's very much important that this BRB is included in IS codes, so that we can have a kind of a standardization, we can have a kind of a quality assurance whenever we are using this BRB. Okay, so these are the few references from which I have collected the material. Okay, so that's all from my side, and now it's over to you. So if you have any questions, doubt, queries, please feel free to share. We will discuss it.
Thank you so much, sir, for making this morning session more interactive and more beneficial for all of us.
Yeah.
You made our concept more clear by touching peculiar topics like performance of steel structure during Northridge earthquake, buckling restraint braces. You also made us aware by introducing Section 12 of IS 800-2007, changes made in NBC to 2016, overview of IS 1893, Part 4, 2015 in an understandable way. Thank you so much, sir. Sir, now with your permission, can we open for questions?
Yes, certainly, please.
Okay, so raise your hand if you have any questions. You can raise your hand if you have any doubts regarding this session. Is there any query?
Sir, I have one query.
Yeah.
Sir, you had mentioned that while designing the connections, instead of taking the forces that are actually acting on the structure, we need to design the connections for the 1 times the plastic carrying moment carrying capacity of the structure.
Yes.
Is it that what?
Yeah.
Because normally when we check, we normally take only the forces into consideration, and we have the sectional properties. Their capacity is much higher than actually the forces that are coming.
Yeah. Yeah. So see what is mentioned in the code. It's first of all, it is not required for all the members. It is required at the location where we see that the possibility of formation of plastic hinge is there. So now let's say in our analysis, whatever we are doing, which is first order elastic analysis. So in that we are not considering this plastic hinge formation. So now whenever we talk about this plastic hinge formation during extreme seismic event, then the forces which will be generated on at that point will be substantially higher. And with that, this clause is introduced in the code, and I agree with your point that it is creating a lot of practical difficulties because it was not the routine practice earlier before this code, wherein we were taking this plastic moment capacity to the picture for the connection design.
Thank you, sir.
Yes, most welcome. Yeah. Okay, any questions are welcome, even if it is out of talk. Whatever points we have not touched, that is also fine.
Thank you, sir, for answering the question.
Yeah.
Sir, it would be great if you can share your PPT with us.
Yeah, sure. Sure, I'll share it.
Thank you, sir.
We'll share it across. Yeah. Yeah.
Okay, sir. Thank you so much, sir.
Okay.
Now there will be break till 12, and we have second session of Dr. DP Soni on seismic base isolation, effectiveness, analysis, and design at sharp 12. So do join the lecture at 12. Now you all can leave the meeting.
Okay, thank you.
Bhavin, for your wonderful presentation.